Hi students, it's Dr. Marks, and our topic for today is keys to good data visualization. Now we're going to be using some data visualization constructs in our upcoming data analysis projects. And so this is something you want to pay close attention to so that you can develop nice graphics that are well crafted and communicate them effectively. Now, in the previous lectures, we've been talking about ways to describe our data through what we've called descriptive statistics. We've talked about things like measures of location, measures of dispersion. We've talked about correlation. But we can also learn a lot about our data through visualizations, right? You've heard the expression, a picture is worth 1,000 words. Well, same kind of thing applies when we're talking about working with data. A visualization can help us communicate a lot of information. So we're going to cover only some of the basics. Understand that the topic of data visualization can take up an entire course, and we just don't have time. But we want to go through some of this information. So this lecture is intended to remind us about tips for good data visualization. But then we'll look at creating some graphics in another lecture. So this topic is really divided into more than one lecture. Now, I know you're familiar with some basic visualization tools. For example, pie charts. We have been working with pie charts forever, right? So here's some sample pie charts. On the left, how much water do we use? Where we're dividing it out, and of course, it should be equal to 100%. On the right, you have something that looks a little bit more sophisticated, right? Most frequently used visuals. And we've got things color-coded. We've got these arrows. Again, a much more sophisticated visualization, but they're communicating the same kind of information. I know we don't need to go through pie charts. You already get this idea, but it would be considered a data visualization example. Another kind of data visualization that I know you've all worked with is bar graphs. And so here's 3 different types of bar graphs. The first one on the left, social media platform use. And you see that big pink spike for Facebook. And I'm guilty too. I like Facebook. I like to sit at night and look through it. So this is a very simple one. Across the horizontal axis, we've got different social media platforms, and we're looking at kind of proportions of use. On the upper right corner, we've got something slightly more sophisticated because now we're stacking data so that we can compare within certain quarters. So this one doesn't have a lot of description about what we're looking at, but we're looking at new revenues, and we're seeing that this gives us, for the same quarter, the opportunity to compare across 4 different entities, whatever those are. And then in the bottom right, we've got a population pyramid, which is just a bar graph. And we're looking at how the population is divided for India. I just grabbed this from year 2014 with males on one side and females on the other. And you see that this is a population that's really skewed towards younger generations, right? Younger age groups. All right. So bar graphs, super easy. We're all very familiar. We're familiar with the line graph. And you see 2 examples here. Both of them have more than one line. They're color-coded. Of course, when we work with colors, we need to have some kind of legend. So we see on the left, we're looking at the unit price filter by brand. Whatever we're talking about here, we've got A, B, C, D, E across the bottom to tell us our legend. And on the right, we see some stock indexes being graphed. So again, line graphs, simple construct. But then you can get a little more sophisticated with things like stacked graphs. And these are interesting because it helps you see the distribution. So there's different ways for you to create stacked graphs, and Excel has options for doing things like this, but there's many more sophisticated data visualization packages you can use. But these are great data visualizations as long as you're being clear and you help the viewer or the reader understand by offering some kind of clear legend and labeling. Let's talk about some keys to good graphical presentations, because I know you've seen stuff that you thought just wasn't very well put together, or might have seemed even manipulated. We'll look at examples of both. The first thing we have to do is choose an appropriate graphical structure that best communicates the data. Not every graphical structure is going to work with every kind of data. So you need to think about what would be appropriate given what your data looks like. Then don't put too much on one graph. It needs to be readable. When we try to shove too much into one graph, it just gets garbled up and nobody can really learn the key points you're trying to communicate. If it's not a good tool for communicating about your data, then it doesn't serve its purpose. Don't put too many lines or too many bars or too many pie segments on one graph, because that, again, makes it ineffective. By the same logic, don't have too many colors. And if you are using colors, it's important to choose colors that are distinguishable. I sometimes have students that turn things in that they use kind of like different shades of, green. And so by the time they put it in a PowerPoint presentation and they show it in a projector, it gets washed out a little bit. And then your viewers and your audience are going to have a very difficult time. Now, 3D can be cool, but it can also be really hard to read. So there's no points for, being extra cool unless it's also readable. So decide if 3D is really useful. Just making something look more sophisticated doesn't really make it more effective in all cases. Of course, don't be misleading and don't misrepresent. That would be also kind of an ethical violation, right? If you're using graphics to distort data, to present things in a way that's misleading. And I'm going to give you some examples and you'll see exactly what I mean by this. Now, when we put together our graphical constructs, we need to make sure that our graph is titled appropriately. And an appropriate title is one that is descriptive. So you might be sometimes too vague. If you title a graph sales growth, that might be too vague. You haven't really told us enough, but maybe sales growth in Eastern region, what year, 2021, or maybe it's 15 through 2021, whatever it is, that might be a better title because you're being more descriptive. Of course, there needs to be a legend provided if you've got more than one entity being compared or you're graphing two things where you have two lines. Legends are going to be key. Of course, your axes need to be labeled with the appropriate units and dimensions. So sometimes I get these graphs and I don't know what's on the vertical axis. Maybe they've plotted over time or over different businesses, but I don't know what the vertical axis is measuring. You have to be very clear. It needs to be labeled. So let's start by looking at some examples of just bad visualizations. And I'm sure that you can take a quick look at these and know exactly what makes them bad. So I found these examples online by other people who had found them. So I've cited them appropriately. But take a look at this craziness. This is a pie chart that goes across a ton of different countries. You see the problem here. Some parts of it are easy to read, kind of, like that really big blue section. Is that China? It seems like it is. The one to the right in the darker blue, is that India? I've got to try to line up these colors. But then as we go around, they start getting really, really small. And I can't figure out, and it certainly seems like there's more different segments than there are entities in terms of these countries. So I don't really know what's going on here. And even if I did, I'm not sure that I can read the data. Also, the colors are a little hard to distinguish. I mean, look at Pakistan, and I'm looking at the legend here, and compare that to Tanzania at the bottom. So Pakistan near the top, Tanzania near the bottom. I don't think I can tell the difference in those colors. So clearly we all agree this is not a good example of data visualization. It's supposed to be population by country, and I don't understand the title, population by country and country. So I'm just at a loss. So again, It might look kind of cool with all these colors, but if it doesn't help the reader, you've not served your purpose. It actually detracts. This might be my favorite example. So these are plot lines. What makes a prize-winning novel? And so you've got these entities on the right. So we've got betrayal, death, love, war. So these things that fan around on the right, the rounded part, are elements. And now they point back to different novels. Now, this is super cool looking. I'm not going to lie. And it's an interesting idea. I do find it a little bit hard to follow. So I find myself like taking my finger and looking at death, and I'm like following the lines and trying to figure out, where they all go. It may just be too much. So how would you solve this problem? Well, maybe divide the themes into two different categories, have two different graphs, so you've got less going on. I don't know, but as cool as this is, I'm not sure it serves its purpose. I don't know what to take from it. Here's another example. We've got sales data, and this is being mapped across the United States. Okay, that's interesting right here. But the problem is that when I look at the map of the United States and I look at the color coding, okay, I can see that, but what I don't really know is what the size of the circles are telling me. Now, I can correlate them with something, but the size just gives me a relative measure. Okay, that's not a horrible place to start. But now I'm trying to figure out, how do these colors, which according to this legend on the right, west, east, central, south, correlate with these other colors down below, because I've got this weird kind of quantity and profit by customer bubble thing on the bottom. Anyway, you see that for one graphical page, there's just a lot going on here. So maybe each section of it is useful, but gosh, cut this up into separate graphs, label each one, talk about each one, talk about just the map, then tell us, now how can I go from this map to then this line, this bar chart on the bottom left, and then discuss it. What are the takeaways? Now let's go to the bottom right. You get the idea. Don't do too much at one time. Walk the reader through what's going on, but make sure we can follow it. And I just don't understand this right here. Now, this is an interesting example. And the problem that we have here is purely one of scale. Initially, there's a second problem, but look at the scale that we have here. We've got this one entity for India that has this really long bar. And because everything else is so much smaller than India, we end up with these little bitty chunks of data being plotted. Now, we've got a legend here. We're doing something here, medical, confirmed cases having to do with, something medical. Doesn't matter. But look at the legend. It says that we've got this blue area, confirmed cases, but that's this teeny tiny sliver of the bar. And then we've got new cases, total deaths, all the way up to these total recovered. You can barely see it, but there's this little teeny yellow section that's right next to red. So the bottom line is that because India is so big, everything else gets scaled together. And against the gray, which is population. So that's one problem. And then second, maybe the colors are a little difficult. So the problem here is that we're graphing population and we're graphing medical cases. And we shouldn't do that in the same graph in this way, because India's got this huge population, but then it's got a teeny tiny portion of that population with confirmed cases, that blue area. So the better thing to do maybe would be to calculate proportions, confirmed cases per 100,000 people, or confirmed cases as a percent of total population. You get the idea. This is really hard to read because of that gray category, graphing population, which then makes everything else really, really small. Now let's move on to talk about some misleading or misrepresentative visualizations. And this may either have been intentional, which I suspect some of these examples are, or just carelessness, but either way, it's bad work. So let's start with this one, and this is an old example. So this is a newspaper that's trying to say that they're leaving everybody else in the dust. So let's look at the right-hand graph where they compare times to the Daily Telegraph. And it makes it look like the Times has more than double the readership of the Daily Telegraph, right? But here's the thing. That Times box, that big black box, might look like it's more than twice the Daily Telegraph, but the thing we need to note is the scale. So look at the axis and how they're graphing this. The axis starts, as I've indicated in that red box, at 420. But it turns out that the difference really isn't that big. It's certainly not more than double. And misrepresentation is that they've started at 420 instead of starting at 0, and that then distorts the comparison between the two. So when we're doing a comparison between two entities, if we don't start at 0 with our scale on that vertical axis, we're being a bit deceptive because it distorts the truth. Here's another example. Now, this one looks like it dates back to the discussion about the marginal tax brackets for federal income taxes during the Bush administration. So we're back in 2013. Doesn't matter that this is an old example. But if you look at it, they're saying, okay, now the highest tax bracket is 35%. That's on the left. And I guess when the tax cuts expire, we're going to be back at 39.6%. And it's showing this huge difference, right? But here's the thing. If we compare a marginal tax rate of 35% to a marginal tax rate of 39.6%, it's only a 4.6% change. But they're making it look like this ginormous tax increase, like the taxes are going to quadruple, right? The way that they've created this graphic is really misleading. Again, why? Look at the vertical axis. They've started at 34, and when they do that, it makes the tax change look like it's huge. And I'm not saying tax changes, where we're increasing taxes are good, but it's not near as large as the graphic makes it look. So again, they're misleading, kind of misrepresenting the reader into going, oh my gosh, this is awful. And, it's awful, but not for the reason shown in the graph. Now, here's another example. And I don't even know what the issue is here, but percent who agreed with the court on some issue that was being presented in the news. And we've got Democrats, we've got Republicans, and we've got independents. And look at the data. Are we seeing the same kind of misrepresentation? Yes. You've got Democrats being, this big column, and you've got Republicans being much smaller. And it makes it look like the Democrats have like triple that of the Republicans or the independents. But again, we have to make the right comparison. When I compare the two, the difference between 62% and 54% is 8%. But that's not what these bar graphs look like, right? Because again, they're starting the data on the vertical axis by plotting starting at 50. So again, what did we say? When we're comparing between, it can be deceptive if we don't bring the axis all the way down to 0, because it makes the differential look a lot bigger than it really is. Now here's an interesting example. We're looking at unemployment rates under President Obama. They pulled their data from the Bureau of Labor Statistics, but this graph wasn't created by the Bureau of Labor Statistics, most likely. And what do we notice here? All right, everything looks fine until we get to this point right here. And I don't know if the intent here was to be deceptive or somebody just messed up, but clearly 9% falling to 8.6% unemployment should not be a horizontal line, right? If we look at the left-hand side of the graph, we see 0.1% changes being fairly steep. So I don't know if there was malintent here or if somebody just messed up, but it certainly offers a misleading conclusion. So I took this data, since it was easy to grab, and I threw it into Excel, and I just made my own graph just to see what the difference is. And look at those last two data points. We see a big decrease in unemployment between October and November of 2011, unlike the graph that was on Fox News. Now, one thing I do want to note is that it can be okay to start your axis not at 0. And in this example, it might be fine because we're not making a comparison between anything. We're not trying to say, oh gosh, one is so much bigger than the other. We're simply showing a trend. And do you agree that if instead of starting at 55, if we started at 0 here, think about what it's going to do. It's going to take this graph and it's going to make it look like it's not changing that much. It's going to just get too small. We're not going to see the ups and downs. But here, I'm simply showing one thing over time. And so this would be appropriate. I don't want you to think that you can never start your axis at a different point. But when you're making comparisons, it's different. Now, just to illustrate, and I'm not plotting the same data because I didn't have access to the data on the left, but I found kind of a similar data set, and I'm showing you that if I start at 0, especially if I have a really big number of observations, then you're going to see that it's going to smooth out. So if you don't start your axis at 55, you might not be able to really see the ups and downs. But again, don't do this when you're comparing between. Now, here's an example. We're looking at an article on receiving federal welfare. And you do see in this graph right here that the axis is not starting at 0. So look at where I've got the blue circle. And you see we're not starting at 0 because it would make it hard to read. But in this graph, if I were to ask you, is this okay? You probably should say, yeah, it's not so problematic because, again, we're just plotting something over time. We are not trying to compare between. But you should always be on the lookout. You need to understand what it is that you're seeing. And so this is important, but not necessarily deception being communicated here. Now, this one I love. Clinical preference study of itch relief. So this was used in some kind of advertisement. So look at this. On the left, we've got hydrocortisone, and I know it's a little blurry, versus Lanacaine. In 1 minute, we see, this big difference. But 60 minutes later, hydrocortisone and Lanacaine, we see a big difference. But what's interesting is that we don't exactly know what's being measured here. They haven't communicated that to us. And we can kind of infer direct action on itch nerves. What does that mean? How is it measured? What's a unit of direct action on itch nerves? So again, we're trying to create this perception for our viewers, but we're not really being that forthcoming in the information. So we need axes, or else it's really hard to know what's being measured. Now, here's an example of a pretty messy graph that came from the Journal of Organic Systems. And this graph, parts of it may be fine, but it's a little messy as put together. And I do want to point out some interesting things to you. So we've got bar graphs being measured and line graphs being measured. So we've got all kinds of things going on this graph. Notice on the right-hand side, if you turn your head sideways, you see that there are two different axes. We've got percent GE corn and soy planted, and we've got glyphosate applied measured in 1,000 tons. So we've got two different axes that are being measured. But we also notice we've got a whole nother axis on the left, incident per 100,000. So we've actually got three different things being plotted with three different axes that are going on here. Now, this graph clearly suggests that there's a strong correlation. The blue line goes up, the red line goes up, the yellow line goes up, but we need to be very clear. That might be okay, but when we talk about this, we need to not suggest causation, right? Remember, correlation does not confirm causation. So we need to make some accurate conclusions from this, not implying that there's a causal story. And if we're not careful, the reader might take or infer a causal story that is not there. So we, as the author of this study, have to be very, very clear about what we can and cannot conclude. Now, there's another problem here that we've just talked about. There are two axes, one on the left and one on the right. Now, the left scale doesn't start at 0. And I suspect that's for a reason, because it makes it align a lot better. There'd be no reason there that they couldn't have started at 0. Why didn't they? Maybe it makes the correlation and possibly inference of causality stronger. But given starting at 0 versus starting at 4, it's going to look different, and it would have fit, right? And we're comparing. So when we're comparing, we really need to start at 0. Now, on the right-hand side, I haven't quite figured out what's going on because we've got a -10. It starts at -10, and it doesn't start at 0. So I'm scratching my head because, again, look at what we're graphing. Percent GE corn and soy planted. Okay, so I guess you're trying to say it decreases, but a decrease usually goes below the x-axis. So it seems like there's some manipulated axes labels here. I don't know enough about organic anything when it comes to agriculture to comment on this, but my instinct is that something was designed to make the graph look a certain way. I can't say that with certainty, but this example is used in a class called Calling Bullshit, and we teach the same class at Longwood University too. It's a class that's offered at a lot of universities, and this is an example. And I'm pretty sure the reason this is part of a class called Calling Bullshit is that this is manipulated data to create the impression that there's a correlation that's stronger than it actually is, because axes start at 0. Negative observations are below the x-axis. Anyway, you get the idea. Now, this is an interesting one as well. What we see here is that real income growth per adult is on the vertical axis. So we're trying to get a sense of what kind of growth have we seen in people's incomes. On the horizontal axis, we're looking at income group by percentile. So we're talking about the lowest 10%, the next 10%, poorest 10%, the next poorest 10%, the next poorest 10%, all the way up to the top 10%. All right, nothing wrong with that specifically. However, all of a sudden on this graph, the scale changes. So let's focus just on the x-axis. We go from 10 to 20 to 30 to 40 to 50, 60, 70, 80, 90, and then we go to 99, 99.9, 99.99. What does that mean? They've taken the edge of that graph and they've stretched it out. That's kind of weird. That's a little sketchy. And look what's labeled here. They're trying to get us to focus on the top 1% of income earners. So basically that 1% that we hear about in the news. But look, they've made them take up this huge portion of the graph. And so by stretching out that x-axis, it puts all this extra emphasis on this top 1%, and it really communicates things incorrectly. So this has clearly been manipulated to try to make the point that the top 1% is capturing, this huge amount of growth, that they have much, more than their fair share of the income. But they create that impression by stretching out that x-axis, and that certainly paints the picture differently. Not trying to say that the top 1% doesn't have a disproportionately large share of the wealth. They may, or the income, they may, but this is not a good way to represent it. This is deceptive. So, my next example is my favorite. So, this actually took me a second to figure out. We have gun deaths in Florida, number of murders that were committed using firearms. You've got data across the x-axis, the 1990s, the 2000s, the 2010s. All right. And I was looking at this and notice right there, they've got a label at 2005 where Florida enacted its Stand Your Ground law. So there's some law. And what do we see happen to the data after that? Murders go down. So it seems, until you realize what they've done with the axis. So what have they done? They have inverted the axis. This graph is actually being represented upside down. So because it's upside down, when we get to this right here, 2005, Florida enacts some Stand Your Ground law, murders are actually increasing because this graph's upside down, right? Murders are going from, 5-something to over 800-something. So this probably wasn't the result that Florida law enforcement officers wanted to see. They probably wanted people to feel like this Stand Your Ground law was impactful. So instead of just owning it, look, at least for a number of years, we didn't see any benefits. They turned the graph upside down. Sketchy, right? All right. So we've just looked at some examples of manipulative data visualization constructs, and some of those issues were data not being plotted correctly, changing the axis scale to not start at 0 when you compare things, making the differentials look very different than they actually are. So now let's wrap up by looking at some not very well thought through visualizations. Here's one I really like. We've got average monthly temperatures in Fahrenheit. Now, this was used to talk about global warming. So we've got temperatures in January, February, March, April, May, June, July. And we see this upward trend. All right. So, is this evidence of global warming? Is this really suggestive of global warming in any way? You should be thinking, well, wait, don't temperatures rise between winter and summer? Because we're in Connecticut, right? Look at the bottom, it says New Haven, Connecticut. So don't temperatures rise between winters and summers anyway? So is that a fair comparison? Temperature goes up between winter and spring, and that is evidence of global warming? I don't think so. And I believe in global warming, but this data doesn't support that. So what would be a better way of trying to support the claim of global warming? Well, you can't look from month to month to month. Maybe we need to look at all Januaries over time, all Februaries over time, all Marches, all Aprils, all Mays. If we can show that over time, January has become a warmer month, and February has become a warmer month. March has become a warmer month. By comparing across the same months, then I might be able to get somewhere, or at least say that we're seeing a trend towards temperatures. Maybe I can't say that's evidence of global warming, but I could at least say, look, this is evidence of a warming planet. All right, let's take a look at the 2012 presidential run. We've got GOP candidates, and we're looking at proportion of, I don't know who, population maybe, that back Palin, that back Huckabee, that back Romney. Now, I know you know how to use a pie chart. So what is wrong with this particular pie chart? Well, what does it add up to? 63% plus 60% plus 70%. This makes no sense, right? Pie charts should add up to 100%. So what's the problem here? If this is accurate data, that this is what I do want to present, that 63% of whatever the population or people in the party back Huckabee and 70% back Palin and 60% back Romney, that's fine. But if this is what I want to communicate, a pie chart's not the best way to represent this, right? And the reason here is that these aren't really shares of a pie. Shares of a pie are generally exclusive categories, right? But here, somebody could back Huckabee and back Romney, or somebody could back Palin and back Huckabee, or could back all three. So these aren't mutually exclusive categories, which means having a pie chart doesn't really make a lot of sense here. So now that we've looked at different kinds of graphical structures, we've looked at different kinds, pie charts, stacked, we've looked at line, we looked at bar, we'll be adding on to that. I know you already know how to work with those. We've looked at some just bad examples of data visualization constructs. We've looked at ones that were deceptive. Now let's just conclude by talking about how do we incorporate these into documents. Remember, you're going to be doing data analysis projects, and you're going to be expected to do a good job incorporating these into the documents, as well as, of course, creating good constructs to begin with. So, first thing is that you might choose to number your graphs and your tables for easier reference. And this is especially true if you have multiple graphs and multiple tables. So it's a lot easier when they're numbered. It makes it easier for you to talk about them. It makes the reader better able to follow you. But a graph is called a figure. So figures. So you would have something like figure 1, estimated quarterly earnings, year 2020. That might be a good title. So come up with some kind of format, be consistent, but we don't call them graphs, we call them figures. Figure 1, figure 2, figure 3. But tables are just called tables. So you're going to have figures and you're going to have tables. Now you need to refer to or point to these graphs or figures or tables if you have them. And what I mean by that is don't orphan them. You need to incorporate them. In other words, the reader shouldn't be reading along and then boom, there's a graph. The reader shouldn't be left to determine why that graph is there. It's your job to tell the reader why the graph is there and what it's telling them. But our in-text references need to come before you get to the graph. So if I'm reading a paper and all of a sudden, boom, there's this graph, I don't know why it's there. You need to have already told me why it's there. And then I take a look at it. So your in-text references need to come before you get to the graph. And then you need to walk the reader through the key takeaways. Now, there is an art to deciding how much to talk about. You don't want to talk about too little. You don't want to talk about too much. So you have to find the balance. So here's an example, and I pulled this from a paper that I did with a school system. So we said number of absences is the dependent variable in the initial investigation. The average number of absences per student is 7.99. However, it ranges from 0 to 78. Chronic absenteeism, 18 or more absences for this particular district, is a problem for 10% of the students, as seen in figure 1. So I'm now pointing to figure 1. Oh, okay, there's a figure here. Great. And I've just told the reader that 10% of students have chronic absenteeism. However, 27.5% of students have at least one absence, missing at least 6.1% of required classes. And I'm telling you, that's another takeaway from this figure. So, bottom line, key points are communicated to the reader here. The figure's not orphaned, and the reader sees this reference to figure 1 before they get to figure 1. Now, there are some citations and plagiarism issues that apply to visualizations. Are you using a graph or a chart from another source where you've lifted it? You can incorporate graphs from other sources, but you must cite it. If you just take somebody else's graph or visual and stick it into your report without citing it, technically you have plagiarized, even if that's not your intent. We solve this simply by citing. Did you use somebody else's data to create your visualization? Well, if you're using somebody else's data, you also have to cite the data source. So you can generally do that below the graphic that you've just created with somebody else's data. For example, I might say graph generated using data from World Bank World Development Indicators available at, and I can give the website. And then, of course, I can put that in my citations. So when you're doing professional work, when you use somebody else's graph, cite it. When you use somebody else's data, and I'm not talking about in your own firm, but external data from some other organization, you cite it like this. Now, for our class, I'm going to be giving you data sets, and you do not need to cite those unless I tell you this data is from another source. If it's data that belongs to me and I give it to you, it could be data I've made up. But if I pull it from the World Bank, I'm going to say, look, this is a data set from the World Bank or the IMF or whatever entity, and then you would need to cite it appropriately. So let's wrap this up. As we've said, good data visualization skills are part of data literacy. We need to be able to put together accurate and understandable visualizations. But in today's day and age, with all this kind of fake news and whether we think news is trustworthy, we have to do our own checking. We need to be able to recognize misleading representations. We want to explain the visualizations we are using for the reader, right? So as we incorporate good visualizations into our work, we need to make sure that we're telling the reader what they should be learning. In other words, don't orphan your visualizations. We've already said that you should be talking about them before the reader gets to that visualization. So don't orphan those visualizations in your data analysis projects. Of course, you need to cite as needed when you're using somebody else's graph or you're using somebody else's data. So thank you so much for listening. Let me know if you have any questions, and have a fantastic day.